I'm going to spend some time talking about radicals. So these are going to be molecules with an odd number of electrons. And this is going to be similar to an unfilled valence, but it leads to some difference in how they react. So an example would be NO2. Nitrogen has 5 electrons, 2 oxygens, each with 6, gives us 17 total electrons. Nitrogen's going to be in the middle, bond out to each of our oxygens, put the lone pairs out on the oxygen. We have a total of 16 electrons there, so we have 1 electron left. It goes on to nitrogen. Nitrogen doesn't have a full octet yet. It's not necessarily not a full valence. We want to get it there, and so this is going to be a radical. And so a radical is wherever we have an unpaired electrons. Every molecule with an odd number of electrons has to be a radical. Okay, so because that's what that means. It's a molecule with an unpaired electron. So this isn't stable. This nitrogen only has 5 electrons. We can improve upon that by turning one of the oxygen lone pairs into a double bond. We get to 7 electrons around the nitrogen, which is better. We can't go more. We can't make a second double bond because now the nitrogen has 9 electrons, and that's no good. 8 is our cap. So we don't want to break 8. We'll see we can for some molecules, but not nitrogen. We'll see why. Nitrogen cannot have more than 8 electrons. So nitrogen has to stay at 7. And so this ends up being a reflective Lewis structure for an NO2 molecule. It's nitrogen, there's a double bond on one side, a single bond on the other side, so it's resonance. But importantly, there's an unpaired electron on the nitrogen, and it is on the nitrogen where it is. And so NO2 molecules are radicals. And so radicals are very reactive. The whole idea of Lewis structure, Lewis theory, we have the octet rules and all these other ideas, but at the base level, the idea is that electrons forming pairs leads to stability. And so if you have, say, a sample of NO2 molecules, they all have unpaired electrons. So it's very common for them to pair up and form what's called a dimer, where basically 2 of the same molecule come together and form a bond. The thing is, these NO2 molecules are kind of awkwardly shaped that this bond ends up just not really being that stable. It's really long. It's really hard for these molecules to get close together. And so they just cannot form a very strong bond. Kind of, you think about 2 kind of big things hanging together. It's just not a really strong connection, and they readily fall back apart. Really, with any sort of heat, they really do fall apart. It's just not a very strong, stable molecule. So these NO2s do exist. If you have a sample of NO2 gas, just like the beryllium difluoride, they can react with each other because they're all unstable in the same way, but they really do exist, these NO2s. And so one of the questions would be, why do they even start, right? One of our questions is, if this is unstable, if we tend to pair up, why does NO2 even exist in the first place? And it forms when you get really high temperatures in air. So naturally it exists from like lightning strikes because you have like a lot of nitrogen in the air and there's also oxygen in the air. And so if you put a ton of energy into those molecules, like say lightning, they'll start reacting. You just start making reactions because you have so much energy. And so atoms just start rearranging, not just kind of changing. Now, that's pretty uncommon. What's much more common is internal combustion engines. When you burn gasoline, nitrogen gets in there, right? You have nitrogen atoms in the molecules in the air. They get into your engine and they start to react with the oxygen that's in there. So you can react and make nitric oxide. That's a radical. Those can react with more oxygen to make nitrogen dioxide. That's a radical. So you make this inside every single internal combustion engine. Generally, it doesn't really get out of the car because you have a lot of, one, it's reactive, so it'll react with other things. But there's also a thing called a catalytic converter at the back of your car that prevents its escape. That if you have a car that's made in the past, say, 3 decades, or 4 decades at this point in time, that is removing those from the air. Because NO2 is really bad. So not only is it really reactive in the sense that if you breathe it in, it's bad for you, but it also will just start reacting with the air. It's also not really that stable of a molecule, as you can probably imagine. And so it'll also fall apart if, say, you have, say, light can hit it. So it doesn't fall apart on its own, but just like a little bit of push of, say, a little bit of light from the sun, you can fall apart. You can create, say, oxygen atoms, which are also radicals, and they create ozone, which is pretty bad for you and much more long-lived. Ozone does have does exist for a much longer amount of time. And if you breathe it in, it can damage your lungs. You'll note an important part of this is car exhaust, especially older cars, but any car will release a little bit, and then sunlight. And so this is why in the summer we have ozone action days here, not too infrequently, in the greater Houston area, because we have so much car traffic that leads to the production of ozone at ground level. And then when you breathe it in, that can be damaging to your lungs. So in general, it's not good for you to breathe that in because ozone reacts with your lungs and does, say, chemistry in there that you don't want to be happening. And what's also really important is that it just kind of feeds on itself. It's a cycle. So even if you don't breathe in the ozone, it can create more NO2 and it can be self-sustaining. When these radicals, if the radicals do get into your body, they create damage by what's called oxidative stress. So oxidative is referring to the oxidation. And we know oxidation is the loss of electrons. Okay, so if you have a radical, this is a molecule with an unpaired electron. That unpaired electron wants a partner, and it will take electrons from other molecules. It will do a reaction where it takes an electron. So it's going to gain electrons really strongly. So radicals are very good oxidizing agents. So radicals naturally are produced in your body. Your body is burning fuel, say, sugars and fuel, and naturally radicals do come about by that. And so your body has molecules that it uses called antioxidants. And the role of antioxidants is to basically take that unpaired electron that's on, say, a highly reactive molecule and move it into a different molecule where it's on an atom where it's not so reactive. A lot of times that's metal cations. It can be other things, though. There are some, say, carbon-based molecules where it can also reside, but that's what antioxidants do. So when, a food product tells you that it's full of antioxidants, they may not be antioxidants that are active inside of humans, which is important to consider. You make your own of these, and so you can use those. This is what you're really trying to use them against, is for to kind of deal with free radicals and prevent oxidative stress. And outside of air pollution, one of the biggest places where we get radicals is from the sun and from UV, right? If we remember UV photons, it's a higher frequency than visible light, so they have more energy. So they have so much more energy that when they come in, if you have really high frequency UV light, it can remove electrons from water. And so if it removes, just instead of exciting the electron, it just kicks it out of the molecule. You're left with a radical version of water. It's had one electron removed from it, so it now has an odd number of electrons. And so you have these radicals of water that are just kind of floating around in your body. And what they will do is just find any other molecule to react with, to oxidize those other molecules, to take an electron from them. And so the big issue, it can destroy like your cells, so like your cell membrane reacting with, say, the kind of structural molecules that hold your body together, which is not good. But also really damaging is DNA, so say the molecules that are, say, controlling and guiding what your organs and tissue do and how they function. And if you start to mess with those things, you can lead to, say, death of tissue, but you can also lead to, say, tissue that doesn't work correctly, starts doing bad things. So these sorts of radicals are really reactive. They are stable in the sense that they don't fall apart, but they really will react with anything else to start removing electrons, to oxidize those things, take that one electron away, because they really want to have a paired electron. And so anytime you have an odd number of electrons, they can't all be paired up, and so you have to have this sort of formation of radicals. All right, radicals. Radical, man. Participation 626, looking for any more questions. Got a handful of videos left. See you next one.